All right, so here's the first problem. It's a square loop and it has a resistance of whatever is that placed on top of a magnet, and the magnet's magnetic field is changing. Okay? And you can see here, this is, what's this symbol there? Flux. And this is time. Okay, so this is a flux versus time graph. And a flux versus time graph, if it's not totally straight, then you can change it. So just looking at this here, we're talking about flux. At which interval in time is the flux not changing? What? Yeah, from 2 to 4, the flux is not changing. So what can you say about the induced current in the loop during that time? 2 to 4. What's that? None is added. Okay, so before, maybe what I should do is I should go back and ask you guys the last time. How do you induce a current in the loop? Changing flux. Okay, so if there is no change in flux, now Melanie, could you answer my question? If there's no change in flux, do I induce a current? No, okay, so there's no induced current. The question is asking, having a resistance of this is placed on top of that. View from above in direction the magnitude of the induced current. So we need to figure out the induced current that we're getting in our loop at these different times. What's the magnetic flux doing here? From 0 to 2. Constant, you're saying speed, but speed is related to position and distance and mechanics. But the flux here, is it changing or not? Yes, it's changing. Is it increasing or decreasing? It's increasing. Then, okay, I'll leave that for now. How about between here and here? Increasing or decreasing? From 4 to 6. What's happening to the flux? Increasing or decreasing? That? Increasing. All right. It is increasing. All right. Which one is steeper? 0 to 2 or 4 to 6? 0 to 2 is steeper. So there's a greater change here than there is here. What's happening between 6 and 7? It's not rocket science, guys. Decreasing. All right. Yeah. Okay, good. So that there are intervals during this 0 to 7 second time frame. There are intervals where the flux is changing. So that means that you would expect there to be an induced current here. You would expect there to be an induced current here. You would expect there to be an induced current there as well. Now, we just need to figure that out. Now, let's draw this and see what we have. Here's my square loop, 4 centimeters by 4 centimeters. I have a magnetic field having a resistance, blah, 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 blah. And then so the magnetic flux is going to be negative at first and then become positive. So it's going to be negative at first. It's going down. Right, there's your flux down. All right. All right. And it's increasing. So it's negative and it's becoming less and less negative until it becomes positive. And then it increases in the positive direction. So let me go back. It's very negative, very downward. Right? It's becoming less and less downward until it becomes positive, and then it becomes more and more positive, right? And then it stays positive. So let's deal with that part first. So here, if we're talking about the change in flux inducing a current, try to remember Lenz's law. Lenz's law is about, what was it again? Can someone remind me? Yeah, it's the law, it's one of the laws of inertia or magnetic inertia, and that nature basically resists any kind of change. So let's try to figure out which direction the change is. So initially, the arrows are very far downward, and then so that's in between intervals 0 and 1. So at 1, is it going to be more? Is it going to be more down or less down? Less down. So it's very down, now it's less down. So what's nature going to want to do? It's going to give you an induced magnetic field in the downward direction. If B induced is downward, which direction is the current need to be going to induce the magnetic field downward? Looking at it from the top, you would use your thumb, going down, loop around. It's what? Which one? Clockwise, exactly. So the answer here would be clockwise. Yeah. It's not going against the magnetic field, it's going against the change. Okay, so it's very down, and then not as down. I didn't like that the down decrease. So it's going to increase it artificially by reducing it. Okay? Yeah, well, initial and final. Yeah, so it really is a change. Okay. All right, from 2 to 4, what's happening there? From time is equal to 2 seconds, time is equal to 1 second. What's happening with my induction? Is there any induction? No, it's just not. Great. So B induced is equal to 0, and there is no current. Last that we find the magnitude, we'll do that. Okay, so from 4 to 6. Tell me which direction the flux is in this, the up or down? Up, because it's positive 2. Is it getting more up or less up? More up. So how is nature going to counteract that? B induced is going to be down. B induced is going to be down. And in that case, if B is down, it's going in the downward direction. Current is going in clockwise or counterclockwise? Clockwise, yeah. Clockwise. All right, last but not least, 6 is which direction is the arrow pointing to? At this time, at 6, or I should say positive 6 at 6 seconds, it's positive 4. So the arrows are pointing where? Up, okay? And are they getting more up or less up? Less up. So how is nature going to counter that? By inducing a field in which direction? The upward direction. So now you use your right hand rule. Up. Okay. So my B induced is upward. My B induced is upward, and I'm inducing a counterclockwise current. All right, now let's take a sample of this and calculate the magnitude. It's asking for direction and magnitude. So we know that E induced, or the voltage induced, is equal to the change in flux as a function of the change in time. All right, so delta phi over delta t. All right, and in this case, it's very easy because they're all linear sections. So we can do it final minus initial. So if we're talking about the interval of 0 to 1, let's talk about the interval of 0 to 1. Okay, what's the final flux? What's the flux at 1 second? 2 minus 2. All right, minus 2. And at 0 seconds, it's what? Minus 6. So that's minus 6. Okay. And the time is 1 minus 0. This is in seconds. This is going to be in Tesla meters squared. So this is going to be minus 2 minus minus 6. So that's minus 2 plus 6. That's what? 4 divided by 1 is equal to 4 volts. Again, that's not what it's asking for volts. It's asking for current. It's telling me that there is a resistance here. So the resistance is going to be, we'll just use Ohm's law. Right? 4 volts. Did you guys get? 0.2 units. Yeah. Let me point your attention to something. The question here is kind of wrong. Let me just point out why this question is wrong. What's fishy about this question? Stop. Is there any information there? Area. Is there something? In what situation would you need to use the area? If I wanted to do this whole thing. Where does area come into play? Why do I even care about area? To calculate flux, but do I need to calculate flux there, or is flux given? Flux is given to me. The question says, placed on top of a random magnetic field whose field strength versus time is plotted on the graph shown below. That part is the part that's wrong. All right, it's not the field strength. If this was B as a function of time, then yes, you would need the area. Okay, so this is a graph for flux as a function of time. You don't need it. Okay, so here 0.2 amps. I'm not going to bother doing the others because it's really just this process done 3 more times. Questions? Good. All right. Example 2 is up to you guys to do it. It is not going to be quiet in here. Start talking. Take markers, work on the. You guys have a mark? You guys have a mark there? You can join these guys if you want. Talk louder so everyone on your table can hear you, okay? I'm doing this. Okay. Okay, what do you mean nothing? Okay, everyone else listening or what? So then now talk louder. Everyone. I'm sorry.
So then the current goes up in a positive
Is the area smaller? Okay. All right. And then what? Okay. No change. Okay. 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 Very good. Your answer is absolutely correct. I'm just going to add a little bit to the explanation. When you have when you have a loop here, and you have a current going, let's say, in the counterclockwise direction, you're just like Shani said, there's an induced magnetic field in upwards direction. All right, and remember, when you have a loop like this and you have a current in it, you're making what's called an electromagnet. So you're going to start creating flux like this. Not flux rather, but magnetic field lines. You're going to create magnetic field lines like this, and this is going to be north, and this is going to be the south, so it's behaving like a bar magnet. All right, and so this is what's happening in the outer loop. It's creating this magnetic field passing through the inside, and always the inside is going to be pointing upwards. And the way we know that is, well, if you stick your finger in the direction of the current, all of the magnetic field lines all throughout is always going to be upward. Okay, all right, perfect. Now that, we know that the magnetic field is going to be going upwards, and the stronger the current, you see the current increase, the stronger the current, the stronger the magnetic field. Okay, if you remember, magnetic field is equal to this equation. It was this equation. So the stronger the current, the stronger the magnetic field. Okay, so that's why you can say that here the magnetic field is increasing, because magnetic field and current are directly proportional. Okay, so that's important. Now we put a loop in there in the middle. So that means we got an area, and that area is going to feel some kind of flux, because these magnetic field lines that the outer loop is creating is going to shove them into the inner loop, right? And as this is increasing, there's going to be more and more flux through that inner loop. So it's going to oppose that increase in upwards magnetic field by inducing a magnetic field downward. So she's absolutely right. That group is absolutely right that the current. So if it's going to induce a current in the downwards direction, it's going to go in the clockwise direction. And the question says clockwise is counted to be as negative. So it's going to have nothing in the beginning, because here the current's not changing. There is no current, right? And then it's going to decrease the current because it's going in the counterclockwise direction. And then it's going to, look at here, there's no change in current, no change in current, no change in no change in no change in flux, and no change in flux means no induced voltage, and no induced voltage means no induced current. Right. So that part stays constant, and then it goes back. Okay. All right. Let's do question 3 next. Okay. So I'm just going to read the question. A long uniform wire is carrying a current with the following function. Right. So what kind of function is this? Parabola, which is a quadratic function. Okay. So if I were to plot it, what would it look like? You said like this. Why not like this? It is like that? You're right.
Actually, no, it's actually like the baboon.
The baboon. What's the trick?
No, well, negative, like, if it's negative, like, the person is bad,
Yeah.
like, exactly.
So yeah. So the graph looks like this. This is current as a function of time. Right? So then here that we need to notice a few things. We know how to, I hope you guys know how to do this, but you're supposed to know that this is an increasing function and then a decreasing function. And you should be able to find the apex of all this stuff using algebra or derivatives if you want. So if I were to just, I'm not going to talk about derivatives. So that's the function of the current. So that means that the current's going, it's going to increase. At a certain time, it's going to decrease until it starts going actually in the backwards direction. So we actually don't know. They don't tell us when the time ends. So it's possible that this goes on forever. All right. So it says here, state the direction of the induced current loop at time is equal to 1 second. So that means we have to find some information about our function. About this I is equal to 100t minus 10t squared. So if we want to find out what the apex is, how do we do that? Yeah. Yeah, so we can find the derivative of I, so I prime of 0 is going to give us the x value for, it's going to give us the x value for the apex. All right, so let's, how do we find the derivative of 100t minus 10t squared? One of the easier derivatives. How do I do that? Yeah. To bring down the exponent multiplied by the coefficient in front, and then you decrease the coefficient, the exponent by 1. Okay? So t to the power of 0 now, and then t to the power of 1. Okay. So this is I prime of t. And Melanie, what did you say about finding that equal to 0? So when this is equal to 0, so 100 minus 22 is equal to 0. Bring the 100 over, divided by 20, so t is equal to 5 seconds. Great. So that means that this apex happens at 5 seconds. Can we say that it ends here at 10 seconds? Yes? Why? Starts at 0. Sure. What we do need to know, what we need to mention is that this is symmetrical. Okay, perfect. So now, it says state the direction of the induced current of the loop at t is equal to 1 second. T is equal to 1 second. What's happening with the current? Increasing or decreasing? It's going to be somewhere around here. Increasing or decreasing? Increasing. So that means that right now, let's say before 1 second, it's going to be, so it's that way with your thumb. Magnetic field lines being produced by the wire are coming towards you. So how do you draw something that's coming towards you? Dot. Dot. X's is away from you, so dot. Right? And I'm going to decrease them as I decrease my height away from the wire, because I is important. The distance from the wire is important, right? So the further you are from the wire, the weaker the magnetic field. So I'm just going to draw them so that there's a lot near the wire, and as I get further and further from the wire, there is a lot less. Okay? But that right now, we're not concerned with. Okay? We're concerned with the direction of the current. So this is that time is equal to just before 1 second. And it's increasing. So at 1 second, it's going to be more of this or less of this? More. So that means there's going to be more at time is equal to 1 second, let's say. We're talking about the change. So was the direction of the magnetic field increasing towards you or decreasing towards you? We need to know this information if you want to find out the loop stuff. Yeah, it's increasing towards you guys. Okay, so there's more arrows coming towards you. More arrows coming towards you means that there is a change in magnetic field. And the change in magnetic field is going that way. So how is nature going to oppose that change? So this loop has to induce a magnetic field in which direction? Mark. They're going to do the opposite. And if the current situation is that there's more coming towards you, so it's going to induce magnetic field into the board. Your B induced is going to be into the board. Okay, now you can use your right hand rule. And so in which direction is the current going? Purple. Okay. Okay, so now the second question is state when the, the direction of the current of the loop changes. What do you guys think? When is it that it's going to stop being clockwise and start being counterclockwise? What do you think?
We're gonna be,
When what's going to be equal?
well, both like, yeah,
First of all, it's not talking about force, it's talking about magnetic field,
yeah.
right? So when is it that this magnetic field here is going to start? Well, actually, let's figure things out. Let's restart from the back, right? Right now, B induced is into the board and the thing is going clockwise. When is it going to be that instead of it going like this, it's going to go like this? And then B induced is going to be up. Right? At 5 seconds. Exactly why? Yeah, it's the apex. And up until here, the current is increasing, right? And all along here, if I were to just draw what the magnetic field looks like, everywhere along this graph, magnetic field induced has always been out of the board, out of the board, out of the board, out of the board. All right, increasing. So I'm going to draw them further apart like that. And as you get closer, there's a higher density. I can just represent it that way. At this time here, is it still, is the current still positive? The current, is it still above the x-axis? So the current is still going that way, right? And the magnetic field is still coming towards you. So it's still that. But it's decreasing. Okay, so it's going to become less and less towards you. So how is nature going to oppose that? It's going to induce a magnetic field in your direction. Okay, so here the induced is going to be a dot. Here the induced is going to be an X. Okay. So yeah, so that means that the direction has to change. The direction of my V has to change, and it's going to be going. The magnetic field is going to be upwards, and therefore the current is going to be going counterclockwise. Take a deep breath because C is a doozy. So the question is, what is the total magnetic flux through the loop at t is equal to 3 seconds? Okay, that's a lot of there's going to be a lot of math involved in this, and I'm going to try to tease out why this is going to be hard. Okay, when I want to find the flux here, right, I need to find the magnetic field that goes through it. And the thing is, the magnetic field changes as a function of how far you are from this wire. Remember that B is equal to mu naught times I over 2 pi r. And this r is the distance from the wire. Okay? So the magnetic field at this point versus the magnetic field at this point is going to be different. Okay? That means that I need to figure out what the magnetic field is at every single, I'm going to call this height, at every single height of my loop. Okay? However, this point and this point, these 2 points, they're going to have the same magnetic field. So that's no problem. That's the easy part. So the left and right is going to be taken care of. But the up and down, we're going to have to use some integration to solve it. Okay? So, okay, we start with this. It's asking you what is the total magnetic flux, which means that it's asking us for phi. And our equation for phi is the surface integral of E dot dA. Okay? Oh, not D. Whoa. Don't be out of B. And if I know this, I can plug that into here. So let's try to do that real quick. We're going to do phi is equal to the surface integral of mu naught times I over 2 pi r times dA. Okay? In this situation, what's constant and what's not constant? So we can take them directly out of the integral, right? You guys tell me. What can I take out of the integral here? 2 pi. Is r constant? R is not constant because whether you're here or here, it's going to give us a different magnetic field. Yeah. Yep, the area is different. We can't take out the area either, but we can take out the 2 pi. What else can we take out? The constant. Anything else? Can I take out the I? Think about it. Can I take out I? Yeah, exactly. I at time is equal to exactly 3 seconds. For that instantaneous moment, yes, it's constant. So I can take I of 3 out of my integral as well. So now I'm just left with dA over R. All right. Now here's my loop. And I need to break it down into little areas because it's asking about little areas. So I can take this little area here, right? And if I add up all of these little rectangles from here to here, I'm going to get the area of the whole thing. Okay? And this area here is going to have a thickness. I'm going to call this thickness dy. Okay? And this here, well, it's easy. I have a length. That's 4L. So let's rewrite our dA. Mu naught multiplied by I of 3 divided by 2 pi integral of length multiplied by dy. And my r, well, my r is also kind of tricky because it's not just any r, it's any r between, well, there's a distance of L here. So we're going to call this any distance from L to L plus, let's call this distance y. L plus y. Okay? And L is actually given to us there. So big L, the length of this thing here, is 3 centimeters multiplied by 4. So this big L, I can write it at 0.12 meters. And this L here is 0.03 meters. Okay, now we could evaluate the integral. I can take this out actually. So it's going to be this mu naught I of 3 times, I'm going to just call this 4L, 4L divided by 2 pi, the integral of 0.03 plus y to the minus 1 dy. And I'm integrating this from 3 centimeters to 9 centimeters. Yeah. 9, because here this is 1 L away from the wire. So that's your lower bound. Your higher bound is 3 L away. So it should be 12, right? Yeah, it should be 12. Sorry. I'm not sure how to solve this integral. Can you guys do it? Work on that. I'm going to rewrite this without all the constants. I combined all my constants to get this value. Tell me if I made a mistake. Does someone have an answer for that integral for me? Do you guys have an answer for the integral? I'm not sure if you can do that. I think you might have to use substitution for this. Yeah. Yeah. Okay. I'll take your word for it. Can someone else confirm what Melanie said? Is this correct? Okay. I'll assume it is. You doing it? The thing is that? And after you evaluate the integral, you get anything? Anyone have an answer for the evaluation? Still nothing? Integral is not right? Okay, I'm not gonna dwell too much time. Figure it out on for the integration. Let's move on to the next problem. Nope. Evaluate the integral. I'm not concerned with your math right now. I'm more interested in your physics. Okay. Yep. Yes, you are. Okay. This is question number 4. You guys do this one? That's been there since yesterday morning. Melanie, your integration is right. Yeah. The answer is what you wrote there. You have an answer? Give me the answer for the first interval. Has anyone done the second one? What do you guys have? Different answers? So let's fight counterclockwise. So tell me your rationale. Nadia, you want to tell me your rationale? Your explanation? Okay. Okay. But what does decreasing mean? All right. So strong into the board to less strong into the board. Okay. So if you're going to use upward. All right.
So if it's strong into the board, then it's less strong into the board.
Yeah.
Oh yeah, yeah.
So it's
But isn't it really
the left.
right? So wait.
The answer is
So it's just the DC or something. No, it's
that's the vector. The vector for this whole area.
Oh. Yeah.
These are all the extras.
Oh, then that's my.
So if we going, if it's going, continuous direction, correct? What is the, tell me about the sorry, so it's decreasing. Is that what you said? I heard decreasing.
It's because going from positive
It's decreasing.
to nature's
Increasing which direction? Into the board. Because it's very much so into the board, and then it's become less into the board. So nature's going to not want it to be less into the board, it's going to want it to be more into the board. So it's going to have that, and then you do it. Right? So it's what? Okay. Oh, no. How about for the third interval? Yeah, okay. Fourth? And the fifth? All right, so I want you guys to tell me, because it's not asking us only about the direction of the current, or whether there is a current or not. It's also asking about the magnitude of the current. Let's do it for this interval here, 20 to 30. Okay, you want to try to find the current at that time. Yeah. I have no idea. Tell me how you got it. If you're going to give me an answer, I want an explanation. Yeah. Okay. Okay.
And then we did this. Then we did this divided by.
Okay, you're missing something. Before that, you're not even at the voltage yet. You're missing something. So what you need to pay attention to is this. It's different from the first question that we No.
the area.
Okay?
Cos pi r squared.
Times pi r squared, yeah. So it's going to be 30 minus 20, sorry, not 30, what am I saying? 0.01 minus 0.01 multiplied by the area, which you said it was pi times r, and r in this case is what? Yeah, we'll do that on the calculator at the end. What's our time interval? How many seconds? 10 seconds. That's going to give us our flux.
Isn't it the voltage?
That's the voltage. That's not going to give us the answer.
I know what you're saying.
Sorry, you're right, the voltage. Yeah, you're right, you're right. What did you guys get for this? For the voltage?
And we got 2.1.
Units? Good. -6?
Yeah.
I got this. Oh, did I make a mistake? 0.02 times 0.02 times 0.02 times pi divided by 12. I got this again. I got actually. Oh, okay. The exponent's 6. Okay, I meant the whole answer is 6. Okay. So that's our voltage induced. And that's all the voltage induced, which is divided by resistance. You divided by resistance, which is 20 ohms. What do you get? Yeah, right.
We got 1.3 times negative.
Sure. If you okay, 1.3. Current units. So that would be the induced current at time is equal to 20 to 30 seconds. Okay? Yeah. It should just be 1. Even here, the answer should have been 1. Just 160. Okay. Just to remind you the kind of derivatives that you guys are going to be expected to be able to do. I want you guys to know how to do the exponential rule. The just regular polynomials I'm talking about, like x to the power of 3 and x to the power of 2, you guys should be able to do that. The exponent rule, basically that the derivative of e to the x is equal to e to the x plus c. So this one is an important identity. And you should be able to know some of the trig ones, namely how to do the derivative of a sine function and a cosine function. I don't need you to know the sine squared and the secant and all those guys, but just the sine and the cosine derivative. For sure, you'll be needing to do that and know how to use the chain rule. Chain rule is how would I? It's like the derivative of the inside multiplied by the derivative. So let's say you have f of g of x, and the derivative of this would be f of x times g prime of x plus f prime of x times g of x. Okay, you guys remember that? No? I'll send you guys a. Okay, I didn't draw this. This was Mr. Rakarsky. I found it in his notes. And he said yay after test one. And then there was a little hump before test two. And then here we are. And it's saying I will not. And he's got no arm. I have no idea what. I think he's talking about the difficulty. But I don't understand. Yeah. Okay, anyways. That's what I have. I have more problems for you guys. There is one I wanted to do absolutely. Now we have. Okay, so there's one I really wanted to do. It's not an easy one. I chose this one because it's a tough one, and I want you guys to have experience with tough problems. So here we go. Okay. Okay, let me explain what's going on here. Here is a square loop. I drew it as a parallelogram to show you just like in perspective. It's actually just a square, or a rectangle rather. The dimensions are shown here. And this thing is spinning from an external force. Let's say it's just me spinning it with my hands. It's not some magnetic force or anything like that. It's like a motor spinning it, and it's spinning it at 4 pi per second, all right? Which means that it's doing 2 full turns every second. Okay, that's what its oscillation is. There is a uniform magnetic field. This should be all parallel, even though it doesn't look like it. Right, there's a uniform magnetic field entering in this direction. All right, and the question is asking you determine the algebraic expression for the induced electromotive force, the induced EMF. Okay, so I want the function for EMF. I want EMF of T, or if you want to call it E of T. Okay. What we need to do is look at this a little bit from the top. And in the question, I write down that the starting position, when you start measuring, whatever, when you start looking at it, is like this. So this is the top view. Okay, and this thing is turning in this direction. Let me ask you a few questions to help us get started. One, is the magnetic field changing? No, magnetic field is not changing. Is the area of my loop changing? No. Is the magnetic, so if the magnetic field is not changing and the area is not changing, does that mean that my flux is not changing? I remind you that flux is equal to is my flux changing? If neither my magnetic field is changing, nor is my area changing. So can you say the flux is constant? What do you think? Okay, yeah, absolutely. So this angle is changing, and therefore the flux is changing as a function of time. This is at some initial time interval, but at some other time interval. Well, first of all, actually, before I say that, what's the flux right now? Is what? Zero, exactly. And then the flux at some time, after some time, is it zero or non-zero? Okay, now it's non-zero because there is, and then at a certain point, this is going to be like this, and the flux is at its maximum there, right? So that's something. So it's going to, so the flux is going to increase until it reaches that, and then it's going to decrease. So what kind of function is this going to look like? So it's going to do this. So tell me if it's zero and max, okay? That's one turn, back to zero. So went from zero to max to zero to max to zero. All right, that's one turn, and then the same thing again. So if you want to talk about the flux as a function of time, it's going to be zero to max to zero to max to zero. That's after one full rotation. Yeah. Yeah. It's a phase, it's a phase shift, and it just matters where it starts. Okay, if it started like this versus if it started like this, it would have been either a cosine or a sine function. So it doesn't matter what we're talking. That's after one turn, so let's continue for another turn. I'll do the same thing after that. Okay. So this is, we said it's 4 pi per second, so this is 1 second, or half a second. And this is 1 second. Okay, because there's 4 pi turns in 1 second. All right. So we've established this. You're right that these two are constant, and Nicholas is absolutely right in saying the angle is changing. Now I need to introduce angle into this in order for me to make it correct. I don't need to worry about b and dA or the integral for that matter. So it's going to be b times a times the cosine of theta. Okay. It's not that simple though, because the cosine of theta is actually what's changing. So this is variable. And I wrote it this way because that's what you're used to seeing. But in fact, that's not the function. The function is actually b multiplied by a multiplied by, and like Melanie said, this is a sine function, right? And it has some angular velocity, omega, written over there, multiplied by okay. You okay with me? You look angry. You're like very expressive with your hands. Okay, so that's just what flux is. So we don't care about the flux. What we care about is the change in flux. So we need to define d phi by dt. Okay, so we need to find the derivative of this with respect to time. Are you guys lost? I see upset people. Is that a yes or a no? W is omega, and it's the angular velocity. How many turns it makes per second? How many turns it makes per second? No? You guys didn't learn this in calculus in grade 11 math? I'm gonna go cry. Yeah, okay, let's learn. It's not that complicated. Did you guys learn about sine functions in high school? Yes, great. All right. So if you have a sine function, right, with a period t, right? You guys remember these terms, right? Or how long it takes to do one full turn, or how much x is y, how much x it takes to do one full turn, right? This is exactly what I'm talking about here. This t is the amount of time it takes to do one full turn. So if it's doing this many turns per second, so it's going to be the number of for a full circle is going to take t seconds, and this is going to be equal to your angular velocity, right? And in this case, for one full second, so for one full turn, it's taking half a second. So I'm saying that my angular velocity is equal to 4 pi per second, 4 pi turns per second, right? And now if I had a sine function, I can't remember I don't know which way you guys learned it, but it was something like a sine ax plus b, no, hx plus k. I don't know, you guys have to help me here. How did you guys learn this? Bx plus k? No, this doesn't ring any bell. What's that? Because we're going to need this when we do LC. So it's not like I'm doing anything above the course. Okay, what can I do? Maybe I can get Mr. Cayenne. I got an idea. Who has graphing calculators? Up your hand. Right. What you're going to do is you're going to graph a bunch of functions. You know how to graph functions, right? Okay, great. You're going to graph sine x, sine 2x, sine 3x. Okay, just do that real quick. All right, forget it. Just do sine x and sine 2x, just so we can compare. What do you notice is the difference between the two? It's what? Right. So which one's more squished? The one that has a 2 in front of the x, or the one that has no 2 in front of the x? The one that has a 2. That means that that number that you put in front of the x designates how many cycles you do per second. Okay? So that's your omega value. I'm losing you guys because not all of you guys are paying attention. So if you were to graph sine x and sine 2x, sine x is going to look like this. Let's just say for one turn. Sine 2x is going to be exactly half of that squishiness. Like that. Okay? So this 2 represents how much x it takes, to do the turn. Right? Or actually 1 over that value is going to tell you how long it's going to take. So the point is that this value here is your frequency. You guys follow me? Right? So 2 in this case is my frequency. So this is my 1 second time, or 1 unit time. And this is telling me in 1 unit time, we're doing 1 full turn. Right? In 1 unit time, I'm doing 1 full turn. And this 2 here is saying in 1 unit time, I'm doing 2 full turns. Okay? So that's what my angular velocity is. How many turns per second? How many full rotations per 1 unit time? Okay? So in that case, if I were to write the expression for this, right? First of all, I need to understand that this is time, right? Because it starts with the 0 and it goes up. Yeah? And that's the compressiveness, or how many turns I'm making per unit time is equal to that variable omega, which I've given to you as 4 pi per second. Okay? All right, that's gist of it. I mean, I think this takes like 3 weeks to teach it in high school. And I just did it in 4 minutes. So I don't expect everyone to understand, and I'm not a math teacher, unfortunately. Essentially, that's how it is. So we set up the equation. Right? Is it making a little bit more sense? Oh. All right, so now what we need is not actually this function. What we need is the derivative of that function. What's the derivative of sine theta? Cos theta. So the derivative of this is going to be not that different. dA cosine omega t. Yeah, I can't take it out of the cosine. Doesn't work that way in you're right. You're right. It's omega cosine. Sure. This is derivative of the inside multiplied by the outside. Yeah. Okay. All right. Now the question was, one, determine an algebraic expression for E of t, and this is it. So E is a function of the electromotive force, a function of time, is equal to omega, which I'm giving to you, times magnetic field, which I've given to you, A, which I've given to you, times cosine omega. Okay? That would be the expression for E and G. So if I were to graph that now on this same graph here, well, I can't really because it's a different axis. Let's say I make a different graph. E and G function time. Yep. Divide by t. Because it's the derivative with respect to time. So I did that by so let's say if I take the derivative with if I take the derivative of plus with respect to time, I take this function and I do the derivative of it, and that already takes into account the change of the function of time. So it's like saying if I have position, and position is equal to 1/2 AT squared plus VOT plus PO. Right? So this is position. You recognize this formula? Really? Position is a function of time, uniform acceleration function. Acceleration, initial velocity, initial position. And this is position at time t. So if I take the derivative of position, for the rate of change of position, I get what? If I take the derivative of position, what do I get? Velocity. So v of t is equal to, now I got to take the derivative of this. So I take the 2, multiply it out in front. So I'm going to get 2 divided by 2. So it's going to be a times t. And subtract this by 1 plus the derivative of this. So it's going to be VO, but I have to subtract it. So there is t to the power of 0. And this one, well, there is no variable. So it's t to the power of 0. And I multiply by 0. So it's going to be nothing. Right? And then I get my expression for velocity as a function of time. But I never divided anything by time. It was in the process of the differentiation that the time was taken into account. Okay? Yeah, the derivative, the definition of the derivative is rate of change. So the rate of change of flux, which by definition is the voltage induced. Okay. Right, last thing, I want you guys to graph this. This is going to look like, so now it's going to have a different shape. Is the amplitude here going to be the same? I'll remind you, in case you forgot, the amplitude of the sine function is the coefficient in front. So is the coefficient in front of the sine function for E induced different from flux? Got it? Yeah, got omega in there instead. So I can't draw a function where it's going to be the same. I don't know if it's higher or lower, but I'll make it that. Right? Actually, it's a cosine function, so let me start off. It's a cosine function, so where does it start with the cosine function? At 0, 0? That's not cosine. Cosine is, it starts at 1, or it starts at the number, the amplitude. It starts at its maximum, and the maximum is designed by this. So it's going to be like this. And it's going to be, let's do 2 full turns. This is 1 full turn, 2 full turns. Okay. Is the time that it takes to do 1 full turn here the same as the time that it takes to do 1 full turn here? Again, the time it takes for it to do that is the value in front of the variable, the variable t. So is the value the same here and there? Yeah, it is. Okay, perfect. This time, this is going to be 0.5 seconds, just like that one. And this one's going to be 1 second, just like that. I kind of didn't draw nicely. So now you can determine what the induced voltage is as a function of time. What does this remind you of? Or what is this? Not what does it remind you of, what is this? A voltage that does this. That's an AC source, all right? And that's exactly what it is. I have something that turns a loop, all right? So I have water pressure, let's say, coming down from a river, turning this thing because it's got flaps or whatever, and I have a magnet shining into that loop, right? And so there's going to be a loop, a current created in this as a function of time. It goes constantly up and down, up and down. Yeah. 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 Sounds good? What do you guys need in terms of math tools? Because I feel like we're not on the same page. So derivative identity, you guys need that. Understanding trig functions. You guys need like a half-hour lesson on that? Okay, I'll do that. So I'll prepare a half-hour lesson on graphing trig functions because we absolutely need that for LC circuits. And then we'll see what's going on. Yeah. Okay. See you. Mark.